Hi guys, I'm coming at you with lesson number 6. I've got a little bit of a mini lecture to help you get started and to complete lesson 6, which is the last part of Anna Garcia's heart health. So we saw in the previous lessons that poor Anna, she has a super high level of cholesterol, right? I think she was at like 398, which is pretty much double what you want to be at. You want to be right around 200. So, one of the reasons why she had such a high level of cholesterol is because she's got this disorder called familial hypercholesterolemia. Whew, kind of a mouthful, but if you break down the words, we know hyper means above, right? Cholesterolemia, meaning cholesterol, so too much cholesterol. And then the word familial right here should make you think of genetics, right? Familial, family, getting passed down from one generation to the next. And that's exactly what FH is. It's a genetic disorder that gets passed down from generation to generation. And what that disorder does is that it makes it so you can't move that LDL, right, the bad cholesterol, the low density lipoprotein, from your blood into your liver, right? Your liver needs cholesterol. It breaks it down and it uses it to make other things. And so LDL should be moved to the liver and then attached to the receptors on the liver and then absorbed into the liver and then broken down and made into other products. But somebody with FH, their receptors either don't work or they don't have enough receptors, and that results in the person having increased cholesterol in the blood and therefore an increased risk of heart disease. So let's see what that looks like. So I found this diagram, and you can see right here we've got our cell membrane here, or this is our um, phospholipid bilayer. Okay, that should be something we recognize. And then right here on the surface of the liver, we have receptors. So you've got these receptors right here. This gives it a little bit of a V shape, and then it allows the LDL particle to attach to the receptor and then get moved inside the liver and out of the bloodstream. Well, over here, people with FH, either you can see there is no binding site or they just don't have enough, right? He's got one little guy over here that works, but there's just not enough of these receptors that are working to function. And so what happens is that this LDL cholesterol stays inside the blood and increases the overall cholesterol. And this liver, who needs cholesterol to start making things, also starts producing more cholesterol. So it's a little bit of a double whammy there. So um, no receptors means the LDL cannot move from the blood to the liver. Okay, so there's a test, a genetic test to see if a person does have SFH, um, and if that's the cause to their high cholesterol. So if you don't know, right, you go to the doctor and you have this super high cholesterol, if they don't know why they have this high cholesterol, you can do a genetic test and see if possibly it is something that is coming from that lack of receptors. So what they do is they take a sample of your DNA, whether it's like a blood test or a swab, and then they have to make copies, right? They find the segment of DNA, that gene that's going to code for a healthy normal receptor, and they're going to make copies of it. So they take a section of the DNA, they find the where that gene is going to code for the protein that makes the normal receptors. And then they're going to use PCR. If you think back to one of our first units when we were doing gel electrophoresis, we said when you have the little piece of DNA, we've got to make copies of it before we can run it through the gel box. So we use polymerase chain reaction, or PCR, to make copies of that segment of DNA. And then we mix that segment of DNA with a restriction enzyme. So that enzyme is going to go through and find a specific site on the DNA sequence, and it's going to make a cut or not make a cut or make two cuts or whatever it is when it finds that site. And so if you look at this little diagram here, this is telling me that if the gene is normal, so that segment of DNA that codes for a healthy receptor, if it is normal, when you mix it with the enzyme, there is no restricted enzyme sites, so you're not going to get any cuts, right? The enzyme is just going to pass on through, boop, 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 boop. It's not going to find any of the sites, and so it's not going to cut. But if you have a mutated gene, right, for the unhealthy receptor, the one that doesn't function, it's actually going to find one restriction site and make one cut. And if we make one cut, it results in 2 fragments. And so there's the difference right there in that mutated gene with one cut and 2 fragments versus a normal gene with no cuts and only one solid fragment. So here's where things get interesting and where we can start to put the puzzle pieces together. We can look at FH, and it is an autosomal dominant trait. So dominant meaning, remember, that not that it's better, but that we only need one dominant allele for the person to have it. Kind of like Best disease. You remember Best disease? So for familial hypercholesterolemia, if your genotype is homozygous dominant, big F, you've got it. If you are heterozygous, big F, little f, you also have it. The only way you have normal receptors is if you have homozygous recessive genotype. So little f is normal. So we can take that and we can apply it to what we know, right? We know that with the dominant allele, right, we've got 2 segments of DNA. One's coming from the mom, one's coming from the dad. And if you get a dominant allele or the dominant trait, big F, one from the mom and one from the dad, the restrictive enzyme is going to make one cut on each side, and you're going to end up with 2 fragments. See, it's going to cut in the same place because it's the same sequence right there. And so you'll have one small fragment, these 2 will stack on top of each other, and then one bigger fragment, and these 2 will just stack on top of each other, right? They're the same size, so they're going to end up stacking on top of each other. Now, if you get a dominant allele, big F, from, let's say, your dad, then that one's going to make one cut. But then if you have the little f, let's say from your mom, that one's not going to cut at all. And so let's see how many fragments we come up with if you are heterozygous. You're going to have one small, right, one medium, and then one that was uncut, one large one. So that if you are heterozygous, you're actually going to end up with 3 fragments. Now, if you are homozygous recessive, little f, meaning both your parents gave you a little f, no cuts on either, so they're going to stack on top of each other and end up with just 1 fragment. So we can use that when we're doing our gel electrophoresis, right? We load the person's DNA into the wells, we turn it on. DNA has a negative charge, so it's going to move towards the positive side. The smaller fragments are going to go further. The larger ones are going to get stuck behind. So we can see that we would expect if you are homozygous dominant, big F, we're going to have 2 fragments. Here's your smaller one. Here's your larger one. Here's your smaller one. And then if you have, let's do little f, homozygous recessive, you're only going to have 1 fragment and it's going to be larger, right? These 2 stack on top of each other and show up as one band. But if you're that heterozygous, you're going to have all 3, right? You're going to have the one large band from the little f, no cuts, and then you're going to have the medium and the smallest fragment from the one cut from the dominant allele. So we can use this gel electrophoresis test to figure out the genotype of a person and see whether or not they have FH. And that is exactly what you're going to do. This is an example. This is not really Anna's pedigree. You actually made Anna's pedigree earlier, but on the lesson 6, there's going to be the results, the gel box results for Anna's family, and you're going to need to create the pedigree and draw it out. Remember, fill in. If it's filled in, that means that they have the trait. So for this one, right, if they have it, it's either going to be big F, or big F, little f. The only way they're not going to be filled in is if they have homozygous recessive little f. Excuse me. So go ahead and you're going to make the pedigree, fill in the genotypes for the people that you do know from the gel box results, but there's going to be 2 people who were not tested. So you have to kind of use your knowledge of what you remember from genetics, maybe make a Punnett square, and go back and try and figure out those other 2 people's genotypes as well. All right. I hope that this helps. And go ahead. I will post lesson 6. It'll be the last one before spring break. And I hope to see you guys soon at our Google Meet, last Google Meet for the next week. And I think that's it. All right. I'll talk to you guys soon. Bye.